Okay, so my name's Acorn, and I'm going to talk about gadgets for games. I've been playing games with Teams Drunken Spider, and running games with Drunken Spider and with Snout. And next slide. So why would you want to make gadgets for games? Next. First of all, they're cool. Next, it gives team members something to do when they're not really involved with solving the clue. Sometimes a clue doesn't involve everybody on the team, and other members get bored. Next, sometimes you can use gadgets to supply hints to teams when you want them to hurry up and get a clue. Next. One of the more important reasons that we use gadgets in Snout is similar to what was discussed in the last talk, skipping teams, and also sometimes directing teams to additional bonus clues or stop, you're going too fast clues. The advantage of using a gadget is that the gadget can based on what time you solve the clue, send you to the next puzzle, or skip you over a puzzle, or skip you over several puzzles, because it knows how far behind you are based on what time you solve the puzzle. Next. And the most important reason to do gadgets for games is it's just fun to make gadgets. Next slide. So what is a gadget? Next. Okay, so for the purposes of what I'm going to talk about, a gadget is a handheld electronic device that's interactive and uses a microcontroller. Microcontrollers are chips that have basically an entire computer built into them, so they're very easy to use, and they tend to be pretty cheap. You can get them sometimes for like $1, $2, $4. In our case, we get them for free. And there's also all kinds of other gadgets which aren't handheld microcontroller-based gadgets, but I'm just not going to talk about those. So next slide. So what goes into a gadget? Next. So first of all, you need some electronics. And next, you need some software. And next, and you need some sort of a case to put it all in. So next. So this can be kind of overwhelming. So the question you have to ask yourself is, where the heck do I start? I think that I have another slide. So I don't know where to start either. So next slide. So the first thing to do is to brainstorm all kinds of great ideas. So come up with cool things that your gadget can do and how can it fit into the game, and all kinds of ideas about what you want it to do. And next. Yeah, things like that. And then next. Okay, so the next thing to do is forget all those ideas, because they're just going to make it too hard to make the gadget, and you're going to wind up not getting all those things done, and you're not going to get the gadget done by the time the game has to run. So a better way to go is to start simple. Next. Yeah. So Hello World is an application or a program that when you're first starting to write programs on a new system, you write this Hello World program, which just prints hello on the screen. And it's a brain-dead basic program, but in order to learn how to take some source code and turn it into an actual program that can run on the computer, you write this very simple program, which is then an example that you use to figure out how to compile the program, how to link the program, how to turn it into something that can actually run. So when doing gadgets, it's a good idea to do kind of a Hello World gadget. So next slide. So what's the Hello World of electronic gadgets? About the simplest kind of gadget that you can make is probably something that just makes a light blink on and off. So I think that's a good project to start with, a good gadget to start with. Next slide. So here's an example of a microcontroller handheld gadget which makes a light blink on and off. You've got basically a battery where the battery is attached one end here and the other end here. And I'm using a PIC 18LF2520 microcontroller, which is, if you're not sure what to start with, it's a good one to start with. Just use it. Or if you want, you can look at they have about 1,000 different PIC microcontrollers, and there's probably 100 other kind of microcontrollers that aren't PIC microcontrollers, and each of those 100 have like 1,000 different varieties. So you can pick one based on exactly what you need, or you can just use this one because I think it's a good one. So once you've put this very basic circuit together, you can go on to make it actually do something. So next slide. So here's an example of the hello world of the gadget software. So I'll just walk you through this. This is code for, again, the PIC 182520 microcontroller. And this is up on my website, which I'll give you at the end too. When you program a PIC, you get the easiest way to do it is to download the free software that Microchip has on their website, and that contains a integrated development environment which allows you to write code and actually run it right on the simulator which is built into the development environment. So you can download this stuff for free and just play around with it and write your software, and it's very easy and it doesn't cost you any money, and it's kind of cool. So this program just starts here. This says start putting instructions at address 0. Here we clear the tri-state B register, which means that tri-state tells the pins whether they're going to be input pins or output pins. So this just says the B port is going to be output pins. So now 8 of the pins on that chip that we saw in the last picture are going to be outputs that can drive a light on and off. Then we'll enter the main loop, and we're going to set a bit, bit 7 of port B, and that basically just turns a pin on. So if you go to the previous diagram, hit the page up. The bit 7 of the B port is attached to the pin in the upper right corner of the chip, and we're going to attach that to a resistor and LED so that when we turn the pin on, the light goes on, and when we turn the pin off, the light goes off. So next slide. So we're just going to turn the pin on, and then we're going to call a function that waits for a little while, and then we're going to turn the pin off, and then we're going to call the function that waits for a little while again, and then we're going to branch back up to here, and we're just going to do that forever. And so this is kind of what the circuit looks like, and you program the code into this chip and put it together, and then you have a light that blinks on and off. Kind of dim. You can also, this is soldered together. You can also build it on a breadboard. These things are handy for trying different things out. And it's basically the same kind of thing. So, and the other part of the program is the subroutine that does the waiting. And to wait is actually, as you can see, it's actually more complicated to wait than it is to do stuff. Waiting is the hard part. So to wait, we set the variable 0 to 0, and we set the variable 1 to 0, and then we decrement it. And these are 8-bit variables, so decrementing it makes it go to 255. And we just spin around doing that until it reaches 0 again. And we come down here and we do the other one. So this basically just winds up waiting about 65,000 loops, which turns out to be about half a second, and then comes back to here. So that's what's going on in these two functions. So next slide. Remember. Okay, yeah. So when you're writing code, having a simulator is really helpful because you can, without having to program the stuff onto the chip or even build a circuit, you can test your code and see what it's going to do. So it's nice to have something like the MP Lab, which has that built in. Next slide. Yeah, go ahead.
Can you burn the chip more than once?
Yeah, so this chip is based on flash. You can burn it about 100,000 times before, well, it's rated for that. You can probably burn it a lot more than that, but it's guaranteed to work at least 100,000 times. So it's pretty quick. You attach it to the programmer. That's my next slide. Oh, I guess not. We'll get to that in a minute. So getting the simulator is free. Getting the chips is free. And so far, making the circuit isn't all that complicated. You might have to know what a resistor is and which way to put the LED in because it's not the same both directions. But so far, it's pretty easy to do this. And the only tricky part is getting the code put onto the chip. So this is the programmer I use. And you just stick the chip in here and you hook this up to a computer and you click the download. Actually, first you tell it to erase the chip and then you tell it to download the program onto the chip. Take the chip out of here, stick it into your circuit, and then you have a blinking light. So when I make gadgets, I recommend first starting out with something really just this simple. Just get something that works at all. And then you can start adding all those cool features that you thought of. And really the most difficult part of building a gadget is just getting to this point. Because once you're at this point, adding features is really easy. And it's also really fun. But getting to this point is difficult if you've never done it before. So I highly recommend just going home and trying this out. And I've got on my website the code and the name of the chip and all this stuff. So you should all have a blinking light by the end of the weekend. And yeah, so this is the slide which doesn't say anything, but it basically just says that this is the thing that you use. Now, there's also lots of other programmers and other types of chips, and you should use those if you like those, or you can use this one. I really don't care. So this thing costs, I think, $200. You can get cheaper ones. You can borrow mine. Also, I find that I like to use Linux for most development, and the MP Lab stuff only runs in Windows. I can run it in VMware, but it gets complicated. There is GNU assembler, GPASM, which you can do development on Linux, and there's also software that you can download which lets you use this programmer on Linux too. So basically, get your basic Hello World program running, and then start adding crazy features. So the next thing, which I don't know if I have a slide for, is okay. I already said all that, I think. Oh, yeah, so I'm probably getting ahead of myself, but one thing that I find is that I use source control. Source control, I see people nodding their heads, but maybe not everybody knows what it is, so I'll tell you what it is. When you're writing code, or you can do it for writing text or anything else too, if you use a source control program, it allows you to check a version of your program into this source control, and then modify it and check another version in, and modify it and check it in. And then the source control remembers all the different versions. And that's very useful because it's very easy to go and add some feature which is really more of a bug than a feature, and then nothing that used to work works anymore. And it's nice to be able to go back and have something that actually works still, even if you're just using that to figure out what the difference is so that you can fix the problem. So the next thing, let's see what the next slide says. Oh, look. Yeah, so I use CVS, but you can use Perforce is free also, I think. And there's other ones. It's also a good idea to use comments which mention what you have working, so that when you've realized that you've completely messed up your program and you're trying to go back and figure out which version you should go back to, this just makes it a whole lot easier. Next slide. Okay, so cases for gadgets can come from all different places. A lot of the time you can just buy stuff. So this is the Magic 8 Ball, which you ask it a question. Does anybody have a question? What am I doing next? Okay. Okay, it's just giving me the alphabet. It's still giving me the alphabet. It likes the alphabet. It says, know your other left. I guess I'm going left next. So this is a case that just bought in a store. Michael's sells these. They're like Christmas ornaments or something. You can paint them and glue shells to them or something. But you can also put microcontrollers and blue LED circuits in them and make Magic 8 Balls. Another way to make cases is vacuum forming. This is the Druid, which has a vacuum formed case. And the way that we came up with this case was I basically built the circuit and made a plaster model of the shape of just the components. And then you can see this has some red clay on it. Basically, I had a bunch of these, and we had a party one day, and I gave everybody a bunch of clay, and everybody added clay to all these things until we came up with a clay shape which looked really cool. And this is the shape we came up with. And then you take this and put it on a table with a vacuum cleaner underneath it. And you take a sheet of plastic and you put it in your oven. And then when it gets hot enough, it starts to kind of sag. And you take it out of the oven and you stick it over the form, which is pretty much looks like this. And you turn the vacuum cleaner on, and it goes and sucks it down, and you get something like this, which is just the plastic sucked over the top of whatever shape you made. And then you can cut this out and glue it together into a gadget. So that's a good way to make a case. Another way to make a case, and I was going to bring the mold, but I forgot, is to, this was also done with clay. So again, I took the guts of the magic wand, and I took some clay and I put it over, and I made what I thought was a really good shape for a magic wand, and I took it and I showed everybody, and I'm like, oh, isn't this cool? And they're like, oh, that looks just like a Marmalade. And it's no good. So I handed it around to different people, and different people tried things, and Curtis got hold of it, and he, made it all mangled and warped, and now it looks a lot more like a magic wand. It's pretty cool. And Microsoft actually took the idea and made their own cases. Also with clay. So the way to take, the way that this case got made, once we had the positive shape that we wanted. I went to Tap Plastics, which is on Castro Street, and got some silicon rubber stuff, and you mix it up, and then you build it. Well, first of all, you build a little box around your positive, and then you mix this stuff up and pour it in on top of your positive, and it dries into this kind of rubbery thing, and then you cut it open, and you take the positive out, and you put a circuit board with wand guts in it into the rubber mold, and you pour some plastic in on top of it. The plastic is molding plastic that's also from Tap Plastics, and you just mix these two parts together and pour it in, and 15 minutes later it's hard, and you take out the magic wand, and then you can paint it or sand it or whatever you want to do.
How much does that cost, plastic?
The plastic costs
just roughly how much per wand did you spend just for the plastic?
Just for the plastic.
The ones themselves are $800.
800 for everything? For the circuits? Okay.
$700, right? For the.
If you're $700 budget, you came in just under 8.
No, it was the other way around. You gave me $800 budget. I came in at 7.
Or somebody owes somebody $100 here.
Yeah, so the wands are actually under budget by $100. So each wand wound up costing about $17. And that includes the free chip, the other free chip, the resistors, which you can get for 2 cents each at Haltech, and the other parts, which cost somewhat more. Probably the batteries were the most expensive part, or maybe the circuit board. Circuit boards are a really good idea to use. The first gadget I did was the Magic 8 Ball, and it doesn't use a circuit board at all, and that's a great option. It looks basically like this. This is 2 of them. You guys can come up and see them up close later, but basically it's just components soldered to a chip holder thingy, and that's the technical name for it. And that works great, but it takes a lot more time to build each one. If you design a circuit board, which you can do with software I use a free program called PCB, and I use a company called Alberta Printed Circuits, and you draw a picture of the circuit you want, and then you email it to AP Circuits, and a few days later they email you back a stack of circuit boards like this, and you cut them up into wand shapes, and then and then you make a bunch of wands out of them. And that's pretty much it. So let's see what's on the next slide. Okay, keep going. Keep going. Oh yeah, you can make a case by just wrapping tape around something too. Often makes a good case. My first wand case was just electrical tape wrapped around hot melt glue. Worked pretty well. Next slide. Yeah, so once you get the printed circuit boards, you can get everybody else in the group to help you manufacture and solder the boards. And it turns out that assembly lines actually do work pretty well. If you get the people who know how to solder to do the soldering, and then the people who don't know anything about electronics to just stick stuff into the board, and it's a good idea to tell them when they have to stick it in one way or the other, then you can get this assembly line going, and it actually goes really pretty quick. You can build a whole lot of gadgets in one night. And then you spend the rest of the week debugging the 3 or 4 or 5 that don't actually wind up working. Or if you're smart, you make enough so that the 3 or 4 or 5 that don't actually work are not really needed. Microsoft was smart and did that when they copied the wand and made the wand. They made like 60 of the wands. We had 2 extras of the wands for Hogwarts, and we needed 3. So probably should have made a few more of those. Next slide. So here's some resources that you can, basically this website has all of the links to MPLab and the data sheet for the chip that I used in this silly blinking light project, which is pretty much the same as the chip in here. I'm not sure what the difference is. And other stuff. And it tells you exactly how to make your blinking light project that you can then turn into the super awesome gadget that's going to be in the next game. And that's it. Any questions? Oh yeah, that's the magic wand. So there's the accelerometer, and this is the microcontroller. It's the 2620, which is the same as the other one, only it's got a 6 instead of a 5. Otherwise, it's identical, I think. And it looks like it's a lot more complicated, but really, like this isn't even there because it's just for debugging. And then these are just connectors, and these are just a bunch of lights that are the lights that you're probably aware of. I don't know if that's working. Yeah. So, and then the accelerometer is actually really simple. You just 3 wires to hook it up. And so you can really do quite a bit with a pretty simple circuit.
Did you get the accelerometer for free?
Can you turn the camera off? Yeah. So it turns out that if you're just doing a prototype for like another bigger run of the project that you're doing, then it makes sense for companies to give you chips so that you'll use their chip, and then you'll buy lots of them when you do the bigger run. So everybody in Team Snout did a little project and requested, I think it was 3 free chips each. And that's how we got our chips. And then the bigger run was Microsoft, because they were funded by Microsoft, and they actually bought the chips. So Microchip, the company, actually came out ahead. And it was worth their while to give us the free chips. Oh, and by the way, the entire magic wand, all the software and the circuit are on my website, and it's open, it's GPL. So if you want to build it, I encourage you to do so.
How long does it take from first concept to finished product?
For the wand?
Yeah.
9 months.
How did that break down time-wise? How much was coding?
It was like a week of electronics and 8.75 solid months of coding. It was a lot of coding. It's 15, is that right? 150,000 lines? I can't remember.
Whoa.
It's a lot of all hands coded assembly, so.
Oh. So did you have any trouble? That fits on a chip, no problem.
Yeah, so the chip that we used holds 64K. I should really know if it's 150 or 15,000 lines of code. I don't remember. It's a lot.
What happens when the battery dies?
You throw it away and make another gadget. So this is the only one that I ever made that has.
I think it's just running a timer for all the last year.
What's that?
I was just wondering, when the battery runs out, so we still have ours from Hogwarts, and I can still pick it up and cast it. And I think during this year, it's just been running a timer, so like maybe like at some point in the game, something transition.
Yeah, so it should last quite a long time. This chip has a power feature that allows you to switch between two different oscillators. There's an internal oscillator that's pretty fast, 8 megahertz, I think. And then this external oscillator is 32 kilohertz. When it's running off the 32 kilohertz clock, it's only drawing about 3 microamps. So the batteries will last about as long as they last on the shelf. Maybe not quite that long. But whenever the lights go on, it's drawing a lot of current, and that's going to use a fair amount. And when you move it, it wakes up and starts looking at the accelerometer and trying to see whether you're waving it and whether it should turn the lights on and stuff like that. Yep.
You want to do a quick wand demo?
Sure. So yeah, I guess, so this is the wand. You shake it to see what it has to say to you. And then to operate it, you first balance yourself, because you have to be balanced to do magic. And then you cast a spell. So I'll cast the cheese spell. Cheese. And now it thinks for a little bit, and then it tells you what you cast. And, oh, it's facing me. Oh, it's casting a spell. Cheese. Or you can do, that's not it.
Do Hufflepuff.
Hufflepuff. Yeah, I'm not even going to try. Dad. Oop. It's not perfect. Oh, I'm not perfect. Dad. Nope, I cast the nope spell. That's the most popular one.
Hey, Acorn.
Yep.
Since you demonstrated that you need to sort of tap the wand to wake it up,
Uh-huh.
would you like to talk about some of the hardware failure modes we saw you run into?
That's a good idea. So we did, during the dry run, since you have to tap the wand to wake it up to start it, we found that teams were like bashing it against concrete columns and smacking it on the ground and stuff like that. So we tried to encourage people to be delicate with their wands, and that they only got one wand, and that if they broke it, then they might get expelled from Hogwarts or something, something bad like that, or perhaps even worse, house points would be deducted. But we did see some failures, which I think that the group up at Microsoft that took the wand and did it, that was more recent, so I remember their failures better. It seemed like the accelerometer was getting desoldered. The accelerometer is this tiny little surface mount chip, which has to be mounted on a tiny daughter board, which is mounted perpendicular to the rest of the circuit board. And it tended to, it turned out to be not that hard to solder that on. But if you just heated the solder and pushed the chip on, which kind of worked, then it would tend to get desoldered. So that's probably the biggest failure mode that I remember. I'm not sure what the other failure modes were. Do you remember what the other failure modes were?
I just remember we got one of the wands back after Hogwarts, and one of the LEDs was actually chipped. It smacked on something.
Yeah, so that's something you have to keep in mind with gadgets. So actually, that's a good point. I was going to mention that. So one of the big problems we had was with the bat blinker. This is a prototype, I think. The bat blinker was popular with most teams, but it was really wet that night, a lot of fog, and the battery was just kind of exposed, and it kind of shorted out, and that wasn't very good. So it's a really good idea when you make gadgets to just cover them in epoxy or plastic or hot melt glue or anything that's going to make it so that there's no moving parts or things that can get damaged by moisture or touching them or anything like that.
Does it work?
It doesn't have any batteries in it. Here's some batteries. I don't know if this one works. What's that? What does it do? Oh, this one. This will. It basically blinks, and you have to figure out what the blinking is telling you.
Wasn't this part of the inspiration for the wand?
This was actually, yeah, so the problem with this is that in order to tell where in the circle the answer is no, this one does not work, apparently. Oh well. Yeah, so the question is, what the heck does this thing do? And the idea is that you spin it around like this, and it's kind of like spinning the wand around like this, and it, well, not like that because it's not doing anything. It paints letters in the air, and the problem with it was that it didn't know where to start the letters in the circle. So it would start them at a different point in the circle every time. There's a little gravity switch on it, which is basically a spring with a piece of solder on it that kind of knocks against another piece of wire. And the idea was that at the bottom of the swing, it would, you'd have the most gravity, and that would cause it to connect. Or what I found was that if you kind of let it, kind of fall over your thumb every time around the circle, so it kind of jerks every time, then there's a few, yeah, that's probably why it doesn't work anymore. That it would work better. But basically it just didn't really work all that well because the gravity switch didn't really work all that well. So I really wanted to make one that worked well, and I figured that an accelerometer would let you know exactly where you are in the swing, but I couldn't really justify having accelerometers in the thing unless I could come up with another use for them. And so I decided to come up with an algorithm for recognizing gestures when you do them in the air. And that justified having a accelerometer so that we could have text that actually stood still. So that was kind of part of the inspiration for the wand. Any other questions? Okay, so if you're interested, there's that website, and if you want to see gadget guts close up, I have a bunch of gadget guts.